How's it going, everyone? Welcome. Julier Gonzalez here. So, let's take a look now at the process of how JavaScript code is transformed, all right? And then we're gonna look at the WebAssembly, that I think that's a very important topic to understand and to read about that, because there is some value on this, and there is a reason why. Oh my God, the author of this book, um, Kyle Simpson, actually wrote about this. And then, well, understand now the strictly speaking, this particular mode, all right? And then now move on to the other topics that are relevant in this case, all right? So let's make a quick recap of this particular chapter, okay? Up to this point, because this is the 2 points that we're gonna take a look here, as well as this. So in the next video, maybe is all of the topic here. So the idea here is to describe is what JavaScript by looking at how the name comes out and who was responsible to write that, the creator of that, which is Brendan H. And from that, the code name of that language where he made that in 7 days was named as Mocha, all right? So internally, this was developed inside of a company called Netscape, the first commercial browser that the name of that script language was known as LiveScript. So the JavaScript is just an artifact of the marketing shenanigans, because it was made and designed to target a specific audience, especially those who are already familiar with the Java language, a very popular language back then in the mid 90s, where this lightweight alternative, it's much more compelling to write this kind of applications rather than the heavy but well-known Java. So since both of language actually assume that you have some background in C, this is the reason why when you know C, you understand JavaScript and so on and so forth, all right? So this background needed for developers is something that make your life much more intuitive to use it. So because the name JavaScript, the trademark, was acquired by Oracle through a series of acquisitions. So for example, Netscape was acquired by a company named AOL, a telecom back in the 90s. So AOL actually, I don't know if AOL exists. I think AOL disappeared, because it was acquired. So through a series of acquisitions, AOL was acquired by Microsoft Systems, a company in 2000. Sorry. A company that in 2009 was acquired by Oracle, and now the trademark belongs to Oracle. But at this point, Oracle hasn't enforced that trademark, and the reality is that this point is quite hard, not to say impossible, to do that. So because the technical specifications is maintained by a commit known as the TC39, so this commit, which is responsible for defining is the technical language specifications known as ECMAScript. No matter how you call this, whether it's ECMAScript or JavaScript or ES2019, you name it, all of these are part of the umbrella term known as JavaScript. All right. So, but the thing here is to identify is what do you mean with this particular topic, whether it's the marketing aspect, the marketing and legal aspect of this, which is the product, the JavaScript, or the technical spec, whether it's ECMA or ES 2019 or the name of the specification, ES, and then in the year of the spec. So the idea is to also understand that this particular commit that gathers to guarantee the all of the JavaScript implementations actually follow a source of truth, a standard, and this committed is made up by several individuals across the entire web industry, from browser makers to device makers like Samsung, and they do this meeting usually 3 days each uh, each month after, okay, so bi-monthly, and some of them can receive some sort of compensation from the company, and it's up to the company to decide where they're gonna host that. Everybody is allowed to contribute to the discussion of the proposals or champions, right? And these proposals or champions, it needs to pass through a several stage, all right? So you can participate to the discussion, but at the end of the day, those proposals or champions that go and meet at the TC39 meetings, all right, they are the only that start the process of going through this stage. That because we are programmers, it goes from 0 to 4, right? So once a champion pass through all of these phases all the way up, right? This process is something that it can take several weeks, months, or even years, all right, to do that. So the idea is to recognize that, especially when you see a particular spec or champion in a spec. Please give me a second here. So, where we are. Alright, so as we now explore about the TC39 commit, who are they? What they doing? What is their main role of in the entire community, and how they lay out several stage to define is all of these different process. You can think of this like a stairway, right? When you have all of these different levels, and when a champion goes through up to when a champion goes all the way up to the top, the stage 4, now it is candidate to actually be implemented by those JavaScript environments. So some of those environments can refuse to implement that due to the nature or the reality of the web. And sometimes now those spec has that the TC39 has promotes, right? They have been to throw back to the drawboard because, for example, when you want to check if a particular element is in a collection, there's a method called now includes. But before the proposal, it was known as the contains. So since there is a particular library that actually make use of that, all right, they have to now rename that functionality. And the other is, I think, the most relevant and dramatic and funny comedy event that happened, known as the Mushgate, where the TC39 approve a proposal, a champion, to flatten is the dimensions of the collections, right? Known as flattening, right? But because there is a particular library that was providing web content for a decent amount of website in Deutschland, uh, so or in Germany. So not only that, because perhaps you can replace that functionality and then override that, and nothing wrong with that, right? It just only is override that. But because that particular functionality in that library also manipulate is the to perform some DOM operations. At the end of the day, what happened is that um, well, you are going to now crash that, and that's exactly what happened. It crashed a couple websites, so they have to go back, uh, do a rewriting of that functionality and call now flat. So that is quite interesting because the idea of that is that the TC39 actually sometimes makes some mistake because they might not know the reality of their web. And for those JavaScript implementations that doesn't or don't want to comply to the spec to implement certain features, there is a particular annex that actually indicate is in detail what is those behaviors that can happen in certain environments. All right. So not only that this particular mismatch, which is the reason of why we actually is, especially new developers, when they get in here to write some codes in a particular environment, whether it is a browser or the server, light bulbs or robots, okay? So they have now this confusion, and I was one of them, that say, hey, but what is this? What is this particular functions that only exists here but not in another ones? And this is because they are host dependent. For example, alert, fetch, unlike fetch is something that you can use in several environments, but fetch, get user media, and get location, get current locations. This is just example of that. Despite that JavaScript is now or has all of these different environments, each one of those environments has their own particularly functionalities. Okay, and once you want to understand how this functionality works, and if you are now a JavaScript language, imagine that you are now a part of the TC39 member, right? And if you want to provide now functionality, and not only is that functionality works across the year, known as backward compatibility, because you don't want to break the web, all right? Unlike, for example, HTML and CSS, which is forward compatibility. So perhaps some code that you write in 1998 won't work in 2025. All right, at least they don't. Is quite likely that they actually show the elements as expected. All right. But because of that, in JavaScript, we want to guarantee that functionality. One, and second is that because the JavaScript community always enforce or promote that we need to write our application using the latest syntax, and I agree with that because it makes yourself familiar with what comes next. And if we want to provide this backward compatibility, there are now tools known as transpiler, which is a fancy way to say I have now code in this high-level language, Python, Ruby, JavaScript, and I want to transform into another one, right? So in our case, since we're writing is code that is at the bleeding edge, okay, or evergreen code. So the idea is to provide that functionality to browser that hasn't been or hasn't implemented that yet. All right. So this backward compatibility is achieved by Babel or any other transpiler. All right. And if you want not to provide this kind of features known as shims or polyfills, you can do that. All right. And it's important to go with the official shims for that. Now, when we talk about this forward and backward compatibility, and because this code, we need to know how that is being executed. We need to know is that JavaScript, how it execute that. Is JavaScript an interpreter language or a compiler language, right? So because historically, computer language that are interpreted has been seen as programs that are not optimized for performance, and they are not robust or mature, like for example compile versions, because compile programs at the end of the day they generate is um, they generate is a binary representation of the program that is portable, that it can be used to distribute that at some point later on in the same architecture, right? Which of course are very, very interesting and very, very powerful. These distinctions right now of what is a compiler language or an interpreter is actually kind of blurry, or that the concept has evolved. And that's true, for example, in JavaScript. So, because this discussion, it all open up a new entire forums and theaters, events to discuss and philosophize that. We want us to know what's the essence of this, which is what is the problem to identify in JavaScript that is a compile or or interpreter language. And the question lies is on how it handles errors. And you may wonder why. Because when you run a particular code, all right, and then you somehow now have some syntax errors, those errors are detected first by the JavaScript engines before actually executing your code. So this is now the process to actually understand what a compile language is, an interpreter language is. First to understand is that an interpreter language, if for some reason you have now 5 line of code and there is an error at line 5, okay, it has to evaluate line by line, all right, until it reaches to the line 5, and this can be now a reference errors or a syntax error, all right. But the problem is that it needs to evaluate that, right? Whereas in compile language, since the entire code is parsed, or in other words, is translate into a internal representation that can be understood by the computer, known as the abstract syntax tree, which is like a map, all right? You can think of this like a map to say, hey, this is the program, this is the set of instructions that we need to execute. I know what is the structure will look like, all right? And then usually compile language, after this step that they generate is the abstract syntax tree, it also generate code, binary code that is ready to be executed. So this binary executable code which according to the architecture, and I don't want to dive deep into that because that's something that is not relevant for that. All right. We want to say is, hey, let's look now at the, just to briefly describe is what are the architecture. So if it's Linux, it's gonna depend on the distro, whether it is on RMP, that's the file name extension for Fedora, .deb, this is the extension for Debian or Debian-like distros, all right? Ubuntu is one of them, and so on and so forth. The same for Windows with the executable or the .msi, or the same is for the APK for Android, or the EPA or .app in iOS, and so on and so forth, right? So the idea of describing this compilation is that this abstract syntax tree, or this different stage that pass, you have the code that is going to parse that into an abstract syntax tree. This abstract syntax tree is like a map, pretty much like when you say, hey, we want to go out to Disneyland or to Dubai or to River, all right? What we want to see is the event at River and Boca, okay? So how that things actually is or works, right? We want to know how we can get there. Let's say we live in provincia, all right? So this particular map help us actually is to understand the structure, all right? So another good analogy is a map that allows you to go through another, for example, Paris. I don't know if you want to go to Paris, but in any case, or the south of Spain, right? When you're gonna see a lot of Moroccans, people from Morocco, and Spanish fighting each other. So the idea is this map, right? That's the internal representation of this abstract syntax tree, and how this abstract syntax tree that has this internal representation, usually compiled language is generated is with this code, okay? So because in the case of JavaScript is a parse language, and this parsing is now something that allows to detect early errors. So for example, syntax errors, all right? But here is what happened when you here's what happened when you, as a developers, understand the entire flow of what happened when your JavaScript code or TypeScript code leave your editor, right? So your JavaScript code is gonna pass now through a transpiling or through a Babel or TypeScript that is going to generate is a particular code that is ready to be interpreted or ready to be understood by JavaScript engines, but before that it is bundled up, all right, using Webpack or any other model bundler, shipped to that JavaScript engine, which is the client or the server, and then it detects that, it parses that, it creates this internal representation known as the abstract syntax tree, all right, and then is the compiler or the internal engine that compile that code and is going to pass through a series of optimizations and refinements known as the JavaScript just in time all right, this just in time uh, interpreter and compiler, right, that once all of the code has been analyzed, all right, then it's going to be executed by the JavaScript virtual machine, right? This JavaScript virtual machine, part of the engine. Okay, so the TLDR of this is that when you know when somebody told you about what JavaScript is, well, you can tell them that JavaScript is a parse language, which in spirit, in fact, or in practically, is a compile language. All right. If you took now the strict consideration of the compiler theory, all right, that is any language that is take now that any language that evaluate that entire code for errors and or evaluate that entire code, generate these internal representations, that after that it output is the code that's needed, the code that can be executed by the machine. So the TLDR of this is JavaScript at the end of the day is a language, is a parse language that in a spirit, that in essence, it might be in practicality, is a compile language, not an interpreted language as we might think. And it is because of the error, how now it detects or how now it runs some early detections. All right. So the point of this is once we're able to understand now, okay, so once we're able to understand is this particular nature of the JavaScript, all right, which is now initially parsed to early detect syntax errors, and then now the JavaScript engine, the compiler generate is a, or this parson generate is now an internal intermediate representation of binary code that is further refined and optimized by another compiler, all right, and it's gonna do that, and the end of that is when it's going to execute that code in by the JavaScript virtual machine, right? So this is the process to understand or to describe for any. I don't think that's for any recruiter, because at the end of the day, recruiter doesn't care about that. What who actually care, or the one who care actually is you. And the reason of reading this is because we want to be now a very competent JavaScript developers to describe and to tackle and to look at a particular problem and be able to describe that, which is another of the phases that the language allows to do, which is JavaScript not only allows to describe problems or approach to problems and solutions in different ways, all right? So, for example, whether it's procedure or object-oriented programming or in a functional way. So the procedure is when you describe now the statement line by line, all right? And then you have now some sort of utilities that you group that into a procedure. The class object-oriented is say, hey, it's going to describe the problems by its data and it is logic into one single unit called class, okay? And this particular class is gonna be used as a way to communicate to that. So anytime that we need to do some particular work, we can do that. And to guarantee that this code is maintainable, it's going to follow some particular principles, all right? So the solid principles, when you say, hey, this unit must only have one single responsibility, the interface must be segregated, interface segregation. The S stands for solid, all right? Which is single responsibility. Anytime that it needs to describe more functionality, I'm going to do that. So I am open to extension and close to modifications, all right? And when I want to now define as subclasses or inheritance, right? So those subclasses must be able to replace is the base class, all right? That's what the list of substitution is. You got it here. So list of substitution is the ability to replace a subclass, the ability to replace a child class with its parent class. Oh, okay. So the list of substitution is the ability for a parent class to be replaced by a child class. I think it is. Okay. Is the ability for a parent class to be replaced by a child class. Exactly. Be able to replace a parent class or a base class with any of its child class or derivative class without breaking the functionality of a program. Okay. So it's the ability to substitute the parent class. It's the ability for a parent class to be replaced by a child class. Okay, but it's that ability. It's the ability for a parent class to be replaced by the child class, the list of substitution, without breaking the programs. All right, which is also interesting for functional programming, which say is that the idea is that performing these functional pure computations, that when you run that, it won't modify the state in an unexpected way of the program, all right? Known as referential transparency. But in any case, the idea of this is, by describing this stand, which is the solid principle, single responsibility, open to extension and close to modification, the list of substitution, the ability to replace a parent class to a child class, for the ability to replace the ability for a parent class to be replaced by a child class without breaking the programs, okay? And the other is the interface segregations to make your life much more simpler when a consumer wants to actually communicate to this particular unit, to this class, all right? And the other is that low-level implementations or dependency inversion is that low-level implementation shouldn't bother as high-level implementations. In other words, there must be an adapter at that particular layer. So the point of this, all right, is that this is now what the class programming style allows you to do. The other is the functional programming, which say he's like, hey, let's now define function, pure functions, that allows to generate is a new computation that the results can be stored in a variable. That variable won't change, right? It's immutable, right? And if you want to a derivative state, you again define as a function that give you these derivative states, and so on and so forth. So this is great because once we're able to look at this and understand this particularly object-oriented or different programming style, the whole point of this is to see how is a particular approach to solve, to look at problems and to solve it, right? And now finally to what we really care about, which is the talking about the strictly speaking and so on and so forth, right? And so on and so forth. So JavaScript is a power language for early detection of errors. So for example, what's the result of this code? So this is a bit. This is helpful. That just. This is helpful. That just any interpreter when it needs to run the code. What the French stuff? This is a bit helpful. Mm-hmm. All right. Yep. Yep. So the process is when you as a JavaScript developer a file and leave the code editor. So the process is when a file, exactly, when a file, okay, so when a file leaves the code editor, okay, so the process is this. So when a file leaves the code editor, it is transpiled for Babel or any other, okay, it is transpiled to a specific version widely executable for when a file leaves the code editor, it is transpiled to a specific version widely executable for many JavaScript engines, and then it is transpiled to a specific version widely executable for many JavaScript engines, and then convert and then bundle up via Webpack or any other model bundler, right? And then bundle up to be sent, exactly, ready to be sent to a JavaScript engine. All right. When the JavaScript code. So when the JavaScript codes arrive, the the JavaScript engine parse it, which is part of the early detection errors. So the JavaScript engine parse it, okay? The JavaScript engine parse it, and create is the abstract syntax tree. This abstract syntax tree is this abstract syntax tree generates a intermediate binary representations of code that is refined and optimized by a just-in-time compilation or just-in-time compiler several times until it is ready. Then the JavaScript virtual machine executes, right? Mm-hmm. Mm-hmm. And there you got it. So after a program leaves a developer's editor, so what's the nitty gritty details boils down. Okay, so what's the nifty so what's the nifty gritty details? So what's the nifty gritty? Interesting. So what's the nifty nitty details boils down to? All right. Step back and consider the entire flow of a JavaScript source program. Mm-hmm. Step back and consider the entire flow of a JavaScript program. Step back and consider the entire flow of a JavaScript program. All right. Oh, okay. Yeah. You're looking for that perspective, and there is nothing wrong with it. So after a program leaves the developer's editors, it gets transpiled by Babel, then packed by Webpack, and perhaps half a dozen other build processes, and then it gets delivered in the very different form to a JavaScript engine. Okay? So when a file leaves the code editor, it is transpiled to a specific version widely executable by JavaScript engines, and then bundle up and then bundle up and then bundle up exactly then bundle up and then it gets delivered exactly, and then bundle ups here, Webpack or any other one, exactly, bundle up and then bundle up bundle up. So then it's bundle up and then it get delivered, and then it gets delivery, or it gets delivered exactly, and then it gets delivered in that way, and it gets delivered in that very different, in that very, and then it gets delivered exactly, and then it gets delivered. So this is why I describe it here. When a file leaves your the code editor, it is transpiled to a specific version widely executable many JavaScript engines, and then bundle up, and then it gets delivered in a very different form to the engine, to a JavaScript engine. All right, the JavaScript engines, exactly. So the JavaScript engine parse it and creates the abstract syntax tree. Okay, the JavaScript engine parse the code and create the abstract syntax tree. This abstract syntax tree generates an intermediate, or is converted. So the abstract syntax tree is converted to an intermediate binary representation of code. Okay, it can be bytecode or any code, which is then refined, that is refined and optimized by a JavaScript, by a just-in-time compiler. Several times. By a JavaScript compiler until it's ready. And finally, the Java virtual machine, which is the engine, executed. Okay, this is now the particularly step-by-step of what's going on in an interpretation, which is not an interpretation, it's just that. It's just a coda. So that is now in Spirit, which is the essence of this JavaScript language, is now a compiler. And then we talk about here briefly of the WebAssembly, right? The WASM. One dominating concern that has driven a significant amount of JavaScript of evolution is performance. Both how quickly JavaScript can parse and compile, and how quickly that can compile code and can be executed. This is one of the concern. That's completely right. This is one of the concern of language interpreted language, or the JavaScript in itself. All right, is how quickly can JavaScript can be parsed or compiled, uh, and how quickly that compiled code can be executed. All right, in terms of this, but it's in terms of this. In 2013, engineers from Mozilla Firefox demonstrate a port of the Unreal 3 game engine to C to JavaScript. The ability for this code to run in a browser JavaScript engine at full 60 frames per second performance was predicted on a set of optimizations that the JavaScript engine could perform, specifically because the JavaScript version of the Unreal Engine code used a style of code that favored a subset of the JavaScript language named ASMG. This particularly feature here, all right, ASMG, right, an extraordinary optimizable low-level subset of JavaScript, and this is the specification. Mm-hmm. I'm not sure is this actually still relevant as it is. You know, AST, type check, pass or fail. If that pass the type check, so you run this and then run check the AST, then call the interpreter. If it failed, AST, link, and the AST, and then call. This is part of the architecture of this ahead of time compilation. Mm-hmm. And how it's going to transform all of this different into a particular value. Not sure is this actually still quite relevant. Build web app compile. Created a script or binary code, creator of WebAssembly, Google opinions my own, not my company. Blue Sky Mastodon links here. Mm-hmm. Holy moly. Works at Google previously, Mozilla, synthesis, mathy stuff. Mm-hmm. Mm-hmm. Krypton. Interesting. Interesting. For your information, I'm not active much on social media, but when I am, it is mostly on Blue Sky these days. Yeah, there is a lot of people that moved to that, right? At this point, most of the tech Twitter that I used to follow is on Blue Sky. Everything is much better there. No ads, good moderation, fast and smooth, better underlying tech, and now it has almost now it almost has most of the people I used to follow, both tech and otherwise. Highly recommended. I have Blue Sky invites if anyone needs one. It is much nicer over there. Good, good, good. But again, it's just subcultures. It's just subcultures. There is nothing wrong with them. So that's interesting. They actually create that. And the using is that. Sakai. Of course. It's getting bombarding of contribution, man. Perhaps also contribution to that WebAssembly binary here. Oh, look at this. Mm-hmm. Oh, they still working on that. Optimizer and compiler toolchains library for WebAssembly. Ah, they working is on the bleeding edge technology here. hmm Okay. Binary is a compiler and toolchain infrastructure library for WebAssembly written in C++. It aims to make compiling to WebAssembly easy, fast, and effective. If binary has a simple C API in a single header and can also be used for JavaScript. It accepts inputs in WebAssembly-like form, but also accepts a general control flow graph for compilers. Fast. Binary's internal ER use compact data structure and is designed for completely parallel code gen and optimizations using all available CPU cores. Binary ends ER also compiles down to WebAssembly extremely easily and quickly because it is essentially a subset of WebAssembly. Effective. Binary ends optimize has many passes. See an overview later on that can improve code size and speed. But it's because of the tool chains using binary as a component. They are the bleeding edge, bro. For more on how some of this works, see the toolchain architecture part of V8 WASM porting blog host. A new way to bridge garbage collected programming language effectively to WebAssembly. Holy hell! A recent article of WebAssembly garbage collection explained at a high level how garbage collection's GC proposals aims to better support garbage collection language in WASM, which is very important given their popularity. In this article, we will get into the technical details of how GC language such as Java, Kotlin, Dart, Python, and C# can be ported to WASM. There are in fact two main approaches. The WebAssembly garbage collection. This was published when? When this was published? Do you have any date? I really hate when they don't have any date. I really hate when they don't put any dates here. There are two types of programming language: garbage collected programming language and programming language that require manual memory management. Example of the former among many more are Kotlin, PHP, or Java. Examples of the latter, they have now garbage collectors that have memory management. An example of the latter are C, C++, or Rust. As a general rule, high-level programming languages are more likely to have garbage collections as a standard feature. In this blog post, the focus is on such garbage collected programming language and how they can be compiled to WebAssembly. Or WASM. So we're talking about here is this WebAssembly, all right? And because a concern is that the compilation, the parsing and the compilations speed has been a concern of JavaScript engines, right? So how fast can JavaScript parse or compile? How JavaScript can parse / compile code, and how fast it can execute that. But it's all about speed here. It's all about speed. In 2013, engineers from Mozilla Firefox demonstrate a port of the Unreal 3 game engine from C to JavaScript. So the ability for this code to run in a browser JavaScript engine at full 60 FPS performance was a predicted of a set of optimizations that the JavaScript engine could perform, specifically because of this JavaScript version of the Unreal Engine code used a style of code that favored a subset of the JavaScript language named ASM. This subset is valid JavaScript written in ways that are somewhat uncommon in normal coding. So they now wrote this subset of JavaScript um, code that is uncommon to what normal coding is, but which signals certain important typing informations to the engine, to the parser, compiler, and the executor of that code. Mhm. ASM was introduced as one way of addressing the pressure of runtime performance of JavaScript. But it's important to know that ESM.js was never intended to be code that was authored by developers, but rather a representation of a program having been transpiled from another language such as C, or it can be JavaScript, where these typing annotations were inserted automatically by the tooling. Mhm. Several years after ASM.js demonstrate the validity of tooling created versions of programs that can be processed more effectively and efficiently by the JavaScript engines. Another group of engineers, also initially from Mozilla, released WebAssembly. WebAssembly is similar to ASM.js in that its origin intent was to provide a path for non-JavaScript programs, C, Ruby, or in any garbage collected language. Okay, for any garbage collected language that can be processed uh, to be converted to a form that could run in a JavaScript. Unlike ASM, was choose to additionally get around some of the inherent delays in JS parsing compilation before a program can execute it. By representing the program in a form that is entirely unlike JavaScript. WAS is a representation format more akin to assembly, hence it is named, that can be processed by JavaScript engine by skipping the parsing and compilation that the engine normally does. Mm-hmm. So, so this subset or this format of code, all right, is now skipping the parsing and the compilation, uh, and the parsing and the compilation of was targeted programs happen ahead of time. What's distributed is a binary package program ready for the JavaScript engine to execute with very minimal processing. So, in other words, it is pretty much like the compiled in the compiler theory. Actually, it is. So, you have now a program that is now generating an abstract syntax tree, which is this internal representation of the code that if everything went well, there and is no error, syntax, semantic, you know, now, um, so for example, there are now token token based. This is token based authentication, but now it is for compiler. Is the holy moly. Um, I am well aware. I am is very well aware of um, of the tokenization, which is this is part of the compiler theory. This is part of the compiler theory. Compiler theory, right? Within the compiler theory, all right, you have now this intermediate representation RM, source code, object, bytecode, machine code, and compilation strategies. Mm-hmm. Compilation strategies here, and notable runtimes, notables compiler and tool change. So is this one. Mm-hmm. Mm-hmm. But I think, yeah, I just want us to um, I just want us to uh, what the French toast is this? Um, mm, exactly. Lexer and parser. Exactly, lexer is a token. It's a lexical tokenizer. Lexer. And it scans compose a sequence of tokens and categorize each of them, for example, as identifier or operators. The latter, alright, sequence is transformed by the parser into a syntax tree, which is then threatened by the remaining compiler phase. The scanner and parsers handles the regular and property context free part of the grammar for C. But after that, exactly, is lexical analysis, syntax analysis, and semantic analysis. This is all done for the front end. And then you have now the middle, which is an analysis, call graph, and all that kind of thing, and optimizations. And then you have now the backend, which is p-hole optimizations and code generation. Compiler correctness. Mm-hmm. Mm-hmm. So, yeah, lexicon analysis. All of these are the things that is happening there. You know, the lexical analysis, the syntax analysis, known as parsing. Mm-hmm. That's interesting. And the semantic analysis. Add semantic information to the parse tree and builds a symbol table. Mm-hmm. Lexical analysis. So large language models build with two difference. First, lexical tokenization is usually based on the lexical grammar, whereas LLM tokenizers are usually probability based. Second, LLM tokenizers perform a second step that converts the tokens into numerical values. And rule-based programs. A rule-based program performing lexical tokenization. It is called tokenizer. But again, what we're doing is just refreshing the compiler theory here, okay? And how now it performed is initially the lexical analysis, okay, or tokenizations. It breaks the source code into a sequence of a small piece called lexical tokens. Okay, this phase can be divided in two stages. The scanning, which segments the input text into syntax unit called lexems and assign it a category, and the evaluating, which convert lexems into process value. A token is a pair consisting of a token name and an optional token value. Common token categories may include identifiers, keyword separators, operators, literal, and comments. Although the set of token categories varies in different programming language, but the thing here is that because it passed through a several step, all right? Because I want to make this now clear of the compiler theory, because compilers, at the end of the day, they are much historically in computing, in the history of computing, they have been uh, saw as much more performance uh, and more robust than it is counterpart and less likely or considered inferior languages, right? uh, Scripting language like interpreter, because from this standpoint it makes a lot of sense, and this standpoint is that, hey, we already have the entire code, all right, all of this script that you perhaps manually or in a computer is being written, right? So you define all of the different instructions that this computer must follow, all right. And once the compiler analyze lexical, run a lexical analysis, which is a fancy way to say, hey, let me not do a token based analysis. This token based analysis is going to identify as keywords, all right, as well as most of the time keywords, right? Most of the time keywords. So continue here to this explanation is that, well, so now that we understand what this machine is doing, all right, which is the compilers, and this compiler is that it takes all of this, you can think of this like page, right? It takes all of these different pages that you define set of instruction on each one of them, all right? And then it's going to analyze this doing a lexicographic analysis, which is the keywords of that, all right, as well as the way of how you create that, the regular expressions, lexical analysis, all right. And once that is done, it's going to now involve which is known as a tokenization. So this lexical analysis breaks the source code into a sequence of a small piece called lexical tokens. So this phase can be divided into two stages: the scanning, which segment the input text into syntactic unit called lexems and assign them as a category, and then evaluate, which convert lexems into a process's values. A token is a pair of consistency of a token named and an optional token value. Common token category may include identifiers, which I mentioned. So because of this lexical analysis, all right, that is breaking down your source code into sequence into sequence called lexical tokens to identify. Now first is through scanning which segment of input text into a syntactic unit, okay, which one of these lexems, all right, or which one of those token consists into a token name and value. That common categories of these tokens are identifiers, all right, so for example variables or labels of that variables, keywords, separators, operators, literals, and comments. And all through the set of token categories vary in different programming language. But the thing is that this remains, this tokenization, that is looking at the source code and scanning and then evaluating those token base, all right, into a category, whether this is an identifier or a keyword or a separator or operators, literals and comments. Although the set of token category varies in different programming languages. So in the case of JavaScript or ECMAScript, it now has a particular way to define this token, to define this category of tokens, right? In the LexSim syntax is typically a regular language. So a finite state automaton constructed from a regular expression and can be used to recognize it. The software doing lexical analysis is called lexical analyzer. The software doing lexical analysis is called lexical analyzer. This might not be a separate step. It can be combined with the parsing step in in a scannerless parsing, in which case parsing is done at the character level, not the token level, right? So syntax analysis, also known as parsing, it involves parsing the token sequence, all right, which depend on the programming language can be this parsing of tokens, which is this unit, all right, which those units are defined by the program, whether it's JavaScript, C, C++, you name it. Those tokens are defined by the programs, and those tokens, in the case of large language models, are defined by those models, all right? I would like to know what is the details in terms of that, you know? What'll be the details on that topic? But in any case, this lexical analysis, which is the process of transforming those source code into lexemes or into tokens that are relevant for the programming language that fell into several categories or buckets, okay? That now, once that is done during the syntax analysis, now that it has all of this token in all of these buckets, it can now create a tree structure built according to the rules of a formal grammar. The parse tree is often analyzed, augmented, and transformed by later phases in the compiler. Semantic analysis adds semantic informations to the parse tree and builds the symbol table. This phase performs semantic check such as type checks, checking for errors, or object binding. But during the semantic analysis, it's going to add now information to the parse tree and build the symbol tables. Interesting. So with all of this, this is ready for the code generation. But the idea here is to understand these different phases that are happening here. And that is that in the compiler theory, this source code is now transformed into, is going to analyze syntactic analysis or lexical analysis, which is going to take that code and it's going to analyze by tokens, whether it's characters or lexemes, which is defined by which is this unit of token, which are defined by the programming language, JavaScript, C. They are who define those units, okay? And those units that fails into a category, typically, they are not identifiers, they are binders, they are operators, they are literals. Interesting, okay? That once that it put in all of these buckets, all right, with that information, okay, of all of these buckets, all right, now the syntax analysis, which is taking all of this bucket information, all of these lexemes, all of this token, all of this uh, units defined by the programming language, pretty much like the unit that we are quite familiar in terms of meters, or in terms of distance, or the times, or the um, weight. All right. So let's gonna use now is the distance. All right. So all of this distance that we are quite familiar, they go from kilometer. I don't know the next one. Ectometer, kilometer, hectometer, meter, uh, the decimeter, centimeter, decimeter, and millimeter. All right. So as long as those source code fell into one of these buckets, all right. Once it analyzed that, then it's going to, once it's do this syntactic analysis or lexical analysis, then it's going to, with that information of all of these buckets, it's going to create now the abstract syntax tree. In other words, is run a syntactic analysis. Holy moly, here. Syntactic analysis. It involved parsing the token sequence to identify the syntax structure of the programs. And this phase typically builds a parse tree, right? It's typically build a parse tree. And I really love about the analogy of these buckets, all right? So once it creates these internal representations based on those buckets, it say, hey, now this belongs to this, and now this belongs to this, and now this belongs to this, and this, and this, and that, and that. So it creates these internal representations, okay? Usually it runs now semantic analysis and then a output from that code generation. I think doing this let me ask this question here. Lord. Give me a second. Give me a second here. Give me a second here. I'll be right. So all of this is just to understand. All right. So all of this is just to understand now what a parse language is, unlike a compile language, right? But that's the idea of this, is because this parsing language is doing this lexical analysis, which is a way to identify tokens or lexemes, which are very specific for programming languages. In our case, JavaScript is this categories that is, hey, is this an identifier? This is a reserved keyword. Is this an operator or a literal, right? Or a comment, okay? And once that is done, it's going to perform now a syntactic you're going to perform a syntactic analysis or syntax analysis for early uh, error detection. And I think this is quite compelling in JavaScript. Very, very, very compelling in JavaScript. Because I will argue that this is a helpful features. At least to identify is this syntax errors. And why we're actually talking about this? Well, it's because that primarily there is now a topic known as WebAssembly that is concerned that the JavaScript in itself, as the web evolved, there is a group of people that are concerned about how performant is this parsing or compiler and the code execution, right? And there were some attempts to now bring a code or port and real 3 games engine from C to JavaScript to run this game to run this game, all right, to allow to run this code in a browser engine at 60 at full 60 FPP performance, and was predicated on a setup optimization that the JavaScript engine could perform specifically because the JavaScript version of the Unreal Engine code used a style of code that favors a subset of JavaScript language named ASM. So this subset of JavaScript features that is somewhat uncommon in normal coding, but it's certain point signals and informations to the compiler, to the parsing, all right? Exactly. To the compiler and to the in some, so it makes key optimizations. So it provides now certain informations to the engines to make it key optimizations. And ASM was introduced as one of addressing the pressure on runtime performance of JavaScript. But it's important to know that ASM.js was never intended to be authored by developers, rather than in a representation of a program that having been transpiled from another language. Several years after ASM demonstrated the validity of tooling created version of programs that can be processed more efficiently by the JavaScript engine. Another group of engineers, also initially from Mozilla, released the WebAssembly. But they now, several years later, demonstrate the validity of tooling created version of programs that can be processed more efficiently by the JavaScript engine. Alright? But this was the first attempt to recognize the concerns about how JavaScript is parsing the code and executing it. Alright? How the JavaScript engine is doing that. And there was now some first attempts with the ASM, which was for 2013 engineerings at that moment, that they say, hey, we can now port an Unreal 3 game engine from C to a JavaScript, and that code now runs on the browser at full 60 fps, making now at full 60p performance, all right, based on a set of optimizations that the JavaScript engine could performs. And this now is a subset of Valley's JavaScript engine that is quite different of how now we program or normal coding, all right. But the point of this is that this subset actually signal or provide informations to do some runtime compilation or optimizations to the JavaScript engine. And again, this was not intended to be this ASM was not to be intended to write. Let me actually take a look at this skill. So the ASM was never intended. Okay. The ASM was never intended to be authored by developers. In fact, it's just as a subset of. In fact, it's just a representation of a program that signal some information or some typing annotations to the JavaScript engines that were inserted automatically by the tooling. So all of this. So as you can see, this is the programming language. It's like, hey, you are now is allocating memory for that, and validation. Did you say use ASM? The ASM sublanguage is defined by a static type system. This can be checked at JavaScript parse time. Interesting. This can be checked as JavaScript parse time. So JavaScript in itself is telling you that it is a parse language. Okay. So for those who don't want to interesting. Okay. Interesting. So the virtual heap represented as type array. So the whole point of this is that here you are now telling to the computer or telling to the putting now some static annotations at the putting some static annotations that were inserted automatically by the tooling. All right. That were inserted automatically by the tooling in there. That is interesting and mind blowing here. Okay. But this is interesting. So ASM, what it's doing is this subset of valid JavaScript language. It was used as a way to address the concern of the language. All right, as a way to address the concern around the language that in terms of performance and in terms of performance. So in terms of how JavaScript can be optimized yeah, in terms of performance, in terms of how JavaScript can optimize the parse and compile, all right, and how quickly JavaScript can parse slash compile, and how quickly now JavaScript can execute the code. So there is a subset of developers at Mozilla in 2013 that they have poured the Unreal 3 game engine from C to JavaScript, and the ability to this code to run into a browser JavaScript engine, right? So this particular code from the Unreal 3 now from C can now run in JavaScript at full 60 FPS, right? Based on the set of performance that we're doing by this subset of the language called ASM. That's what it's doing behind the scene, is just adding some additional informations to the engine to run some of optimizations. So as a way to address the pressure, or as a way to address it, is the pressures of runtime performance of JavaScript. This particular subset of valid JavaScript, which is different from what we normally code, right, was not known as ASM.js, was not intended for authored was not intended to be written by developers or authored by developers, but rather a representation of a program's having been transpiled to another language, such as C, where these typing annotations were inserted automatically here. And this is interesting. Several years after ASM demonstrated the validity of the tooling, created version of a program that can be processed more efficiently by the JavaScript engines. Another group of engineers, also initially for Mozilla, released the WebAssembly WASM. WASM is similar to ASM in that the original intent was to provide a path for non-JS programs, for non-JS programs, okay, whether it is that has garbage collector or not. C, you have to manage the memory for yourself. C, C++, Kotlin, PHP, and I don't know, to be converted to a form that could run in the JavaScript engine. All right. Unlike ASM, WASM choose to additionally get around some of the inherent delay in JavaScript parsing compilation before a program can execute, by representing the program in a form that is entirely unlike JavaScript. WASM is a representation format more akin to assembly. So because now in terms of actually define that subset of language, unlike ASM, that adding some instruction or some annotations that were automatically inserted by the tool to notify the JavaScript compiler or engines to run some optimizations. Unlike the ASM, WASM have the similar goal in a spirit. It's similar to say, hey, let's go to now migrate is any JavaScript non-JavaScript programs written in C, Rust, C++, into a code that can be run in JavaScript. And this code, unlike ASM, was choose to get around some of the inherent delay in JavaScript parsing and be now a more representing that code into a different format, in represent that code into a different form of JavaScript, more like a web assembly, more like assembly, when you have to move register in one place to another. And that can be processed by a JavaScript engine by skipping the parsing and compilation, all right, that the JavaScript engine normally does. So in other words, the engine in itself, that when it receives this source code, it's going to now run a lexical analysis, a tokenization of that, and it's going to put all of those categories defined by the language into particular buckets, whether it's keywords, identifiers, uh, whether it's this token base, which is the token name and the value, all right, and put now in all of these categories or buckets here, whether it's this, hey, is this represent an identifier? Is this a operator? Is this a comment? Is this an identifier? Okay. And then, all right, and then it says, all right, now let's take a look at the way of how can we create a internal representations to run some static syntax analysis, all right, which is the for early detection errors, the syntax errors is doing that before actually generating a code for that. Because JavaScript, and as we mentioned, we want to skip is this parsing phase. WebAssembly is now a representation that is looks like as assembly. Holy moly! So the parsing and compilation of a WASM targeted program happens ahead of time. Was distributed in a binary pack form, ready for the JavaScript engines to execute with a very minimal processing. So not only that is skip the parsing phase, all right, by actually describing is this code in a way that is in a way that have to skip the parsing phase, all right, this tokenization, the syntax errors, all right, and it's going to generate is a binary representation that is ready for the JavaScript engine to be run. Holy fuck. mm-hmm. Mm-hmm. With very minimal processing. An initial motivation for WASM was clearly the potential performance improvement, while that continues to be a focus. WASM is additionally motivated by the desire to bring more parity for non-JavaScript language to be web platform. For example, if a language like Go, if a language like Go support thread programming, but JavaScript language does not, WASM offer the potential for such a Go program. An initial motivation for WASM was clearly the potential performance improvement. While that continues to be a focus, WASM is additionally motivated by the desire to bring more parity for non-JavaScript language to the web platform. For example, if a language like Go supports thread programming, but JavaScript clearly not, the language doesn't. So it's a particular feature that is providing. Okay, if a programming language support a feature that another doesn't, or that JavaScript doesn't, WASM offer the potential for such a program Go to be converted to a form the JavaScript engine can understand without needing a thread feature in the language itself. In other words, WASM relieve the pressure to add features to JavaScript that are mostly exclusively intends to be used by transpiled programs from another. language. That means JavaScript features developed can be judged by TC39 without being skewed by interest demands in other language ecosystems, while letting those languages have a viable path on the web. Another perspective on WASP that's emerging is interesting, not even directly related to the web. WASP is evolving to become a cross-platform virtual machine of sort, when programs can be compiled once and run in a variety of different system environments. This is another perspective of WASP that is emerging, interesting, not even directly related to the web, but that it becomes like a cross-platform virtual machine of sort, where programs can compile once and run in a variety of different system environments. So WASP isn't only for the web, and WASP also is in JavaScript. Ironically, even though WASP runs in the JavaScript engine, the JavaScript language is one of the least suitable language to source WASP program with, because WASP rely heavily on static typing information. So WASP isn't only for the web, exactly. It has now a perspective that becomes a cross-platform virtual machines where source programs can be compiled once and run in a variety of different system environments. So tell me, where is the target? Tell me what is the target system? Interesting. Tell me what is the target system. All right. Ironically, even though was run in the JavaScript engine, the JavaScript language is one of the least suitable language to source WASP program. With because WASP rely heavily on static typing information. Even TypeScript, ostensibly JavaScript plus TypeScript static type, is not quite suitable as is a stand to transpile to WASP. Though language variants like AssemblyScript are attempting to bridge the gap between JavaScript and TypeScript and WASP. This book isn't about WASP, so I won't spend much more time discussing it, except to make one final point. Some folks have suggested WASP point to a future where JavaScript is excised from or minimized in the web. These folks often harbor ill feels about JavaScript and want some other language, any other language, to replace it. Since WASP lets other language run in the JavaScript engine, on its face, this isn't an alternative. This is an entirely fanciful fairy tale. But let me just state simply, WASP will not replace JavaScript. WASP significantly augments what the web, including JavaScript, can accomplish. Exactly. That's great things, entirely orthogonal to whether some people will use it as a escape hatch from having to write JavaScript. And then we are looking here, strictly speaking. Back in 2009, with the release of ES5, JavaScript added strict mode as an opt-in mechanism for encouraging better JavaScript programs. The benefit of the strict mode far outweigh the cost, but all habit diehards and the inertia of existing, aka legacy, code bases is really hard to shift. So sadly, more than 10 years later, strict modes optionally means that is still not necessary the default for JavaScript programmers. Why strict mode? Strict mode shouldn't be thought of as a restriction on what you can do, but rather as a guide to the best way to do things so that the JavaScript engine has the best chance of optimizing and efficiently running the code. Most JavaScript code is worked on by teams of developers, so the strictness of the strict modes, along with tools like linters, often helps collaboration in code by avoiding some of the more problematic mistakes that slip in non-strict mode. So most strict modes controls are in the forms of early errors, meaning errors that aren't strictly syntax errors but are still thrown at compile times before the code is run. For example, strict mode disallows naming two functions parameter the same and results in an early error. Some other strict mode controls are only observable at runtime, such as how this default to undefined instead of the global object. So other strict modes controls are only observable at runtime, such as how this default to undefined instead of the global objects. Interesting. Most strict modes control are in the form of early error, meaning errors that are strictly syntax error but are still thrown at compile time before the code is run. That's interesting. Alright, so at the you are now enhancing the parsing here. Mm. Okay. To enhance that as it is. Mm. Mm-hmm. Mm-hmm. So what you're doing is now you are enhancing with strict mode is the uh, the common errors that the language has, and to prevent that and detect that at parse time. Okay, and detect that at parse compile time. For example, strict mode disallow naming two functions parameters at the same. Strict mode disallow naming two functions parameters the same. Two function parameters the same, and result in an early error. Interesting. Let me run to this. Let me run into this. Say it's a function here. Say you say for example now function fruit list, and you say now disallow naming two functions two naming two function parameters the same. Say a fruit and a fruit, right? And if I say something like this, you can say console log is the fruit, right? And if I say now here, this is a definition, and if I say now is fruit fruitless, and then I pass now this, right? And put this apple. Let make my life simple. B and C, let make my life simple, bro. Let make my life simple. And then I pass another thing like this. C and B and A, right? However, well, it's using the. However, you do the use a strict. And if you do something like this, it doesn't throw that error, bro. In fact, it allows you to do this. Again, this is a JavaScript friendly environment. Use a strict. Okay. Interesting. Duplicate name parameters not allowed in this context. Very subtle stuff, but yet important for, again, very subtle stuff, but yet important as a JavaScript developer. So I'll make a pause here. I'll be right back. All right, and we're back. Now, wait a single moment, please. I'll be right back. And we're back. Now, so I think this last 2 hours has been very, 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 very relevant, eye-opening, and very, I mean, perhaps I don't have the words to describe all of the feelings that I have passing through, but yet I can describe is why am I doing this and understand, because all of the things that we have learned so far is just to understand, and just to understand that how do we get here, what is this, and how can we now wield this tool, right, this weapon, without cutting ourselves, and not only ourselves but millions of people, without cutting them, and also to understand what is now the advancements and the constraints and the benefits of the language, right? A huge overview, and be able to describe that in this story, because it makes sense of the world. We make sense of the world through stories, despite that some of those stories might not actually accurate to describe the reality of the nature, which is what happened with a lot of this religions and society and stuff that we say, all of this recipe that we need to do and follow and so on and so forth. But at least for the technical aspect, like this, or even though in sports or in music, for those mechanical, technical stuff that can be replicated, can be described, this is something that is, these particular recipes are helpful. And when you want to now understand more the truth, especially if you are now not only a JavaScript developer or any that is relevant in the software field or on the athletes or music, there is now a point that by definition, that if you want to be somebody that is at the top of that realm, there is no guidelines, there is no rules, there is none of that. And I brought that out because this is the reason why I'm doing this. I'm doing this is for myself. Make no mistake. I'm not doing this for an audience. I'm not doing this for somebody else. No. I'm actually doing this for myself. And then me from the future can look at that and say, good, great, and move on. All right. So we were now at the strictly speaking. Okay. So the benefit of the strict mode far outweigh the cost, but the old habit died hard. As I mentioned previously, I just want to reread this, all right? And that's quite interesting, bro. And that's quite interesting that actually when I use this, it throw a particular error, bro. And it's using is the last one, and is using is the last one. All right. and is using is the last one here. Alright. So why strict mode? So strict mode shouldn't be thought of a restriction on what you can do, but rather as a guide to the best way to do things so that JavaScript engine has the best chance of optimizing and efficiently running the code. So you are now running a code that can now JavaScript engine can efficiently parse and or can efficiently run optimizations on your code, right? Has the best chance of optimizing and efficiently run code. So most JavaScript code is worked on by teams of developers. So the strictness of the strict mode, along with tools like linters, often helps collaborations on code by avoiding some of the more problematic mistake that split by in non-strict mode. Most strict mode controls are in the form of early errors, meaning errors that aren't strictly syntax errors, but are still thrown at the compile time, the parsing time. Alright. For example, strict mode disallow naming two functions parameters the same and result in an early error. Some other strict mode controls are only observable at runtime, such as how this default to undefined instead of the global object. Rather than fighting and arguing with strict mode, so for example, strict mode is allow naming to function parameters the same and result in early errors. Some other strict mode controls are only observable at runtime, such as how this defaults to undefined instead of the global object. Rather than fighting and arguing with strict mode like a kid who just wants to define whatever their parents tell them to not do, the best mindset is that a strict mode is likely a linter reminder you how JavaScript should be written to have the highest quality and best chance at performance. If you find yourself feeling handcuffed trying to work around a strict mode, all right. All right, and to finally wrap this particular section, all right, of the strictly speaking, strictly speaking, okay. Rather than fighting and arguing with strict mode like kid who just wants to define whatever the parents that tells them to not do, the best mindset is the strict mode, not the best mindset, the effective, what is permanent is that use the linter, okay, is use a strict mode as a link to understand why the strict mode is as a linter reminding you how JavaScript should be written to have the highest quality and best chance at performance. If you find yourself feeling handcuffed trying to work around strict mode, that should be a blaring red warning flag that you need to back up and rethink the whole approach. Strict mode is switched on per file, which is a special pragma. Nothing allowed before it except comments and white space. You can do this, and the rest is on the files run on a strict mode. Warning: something to be aware is that even the stray.com all by itself appearing before the strict mode pragma will render the pragma useless. No error are thrown because it is a valid GS to have a string literal expression in a statement position, but it will silently not turn on the strict mode. Strict mode can alternatively be turned on per function scope with exactly the same rules above its surroundings. Interesting, if a file has a strict mode, turn on the function level strict mode pragmats are disallowed. So you have to pick one or another. The only valid reason to use a per function approach to strict mode is when you are converting an existing non-strict mode program file and need to make the change little by little over time. Otherwise, it is vastly better to simply turn strict mode on the entire file program. Many have wondered if there will ever be a time when JavaScript makes strict mode the default. The answer is almost certainly not, because they don't want to break the web. As we discussed earlier in backward compatibility, if a JavaScript engine update start assuming code was strict mode, even if it is not marked as such, it is possible that this code will break as a result of the strict mode controls. However, these are few factors that reduce the future impact of this non-default obscurity of a strict mode. For one, virtually all transpiled code ends up into strict mode even if the original source code isn't written as such. Most JavaScript code in production has been transpiled, so that means most JavaScript is already adhering to the strict mode. It's also possible to undo the assumption, but you really have to go out of the way to do so. So it is highly unlikely. Moreover, a wide shift is happening toward more or most new JavaScript code being written using the ES6 model format. ES6 model assumes strict mode, so all code in such a file is automatically default to strict mode. Taken together, strict mode is largely the de facto, even though technically it's not actually the default. And define. JavaScript is an implementation of the ECMAScript standards ES 2019 of this writing. Right now we are at the 2025, which is guided by the TC39 committed and hosted by ECMA. It runs in browsers and JavaScript environments such as Node. JavaScript is a multi-paradigm language, meaning that the syntax and capability allow a developer to mix and match and bend and reshape concepts from various major paradigms, such as procedural, object-oriented programming, and functional programming. JavaScript is a compiled language, meaning the tool, including the JS engine process and verify a process. And JavaScript is a compiled language, parse compile language, meaning the tools, including the JavaScript engine, process and verify a program, which is reporting errors before it executed. With our language now defined, let's start getting to know the ins and outs of this. So that's quite interesting. There's also mind-blowing of all of this. And that'll be all for this video. Take care. Bye-bye.